Now let me show you another application of combinatorial stanzas. So this is due to Noga alone. So we have a prime p, an odd prime, and we have integers, not integers, numbers, and up to ak and b1 of the pk numbers, and let's say k is less than p. We want to prove the following. If b1, b2, bk are distinct, then there exists a permutation pi of one of the k such that a1 plus b pi 1, a2 plus b pi 2, ak plus b pi k are all distinct. Right? So whenever you have a k numbers and another k numbers, if this another k numbers are all distinct, then I can pair them up so that their sums are distinct. Right, so that's the theorem. And this uses combinatorial Null-Strange, so we need to define a polynomial in order to use the Null-Strange. So let's define f of x1, x2, xn as follows. So product of xj minus xi, then product of xj plus aj minus xi minus ai. All right, where this be a polynomial over build of p elements, right? So everything is modulo p. Now we will take Li to be the numbers b1, b2 up to bk for all I. Right? So our goal is to our goal is to find an assignment of xi so that this f is non-zero. Okay? So we are proving, like, for instance, x1 could be b1, x2 could be b2, etc. And if this polynomial is non-zero, what does that mean? So f, or let's say b, if x1, x2, xn is non-zero, that means xi is not equal to xj for all distinct ij, right? Because of this term. And because of that term, what does that mean? That means xj plus aj is not equal to xi plus ai for all I different from j, right? So this means, well, they are different, and there's some pairwise sums are different. And right, so our goal is to find an assignment of xi's by bi's. I mean, since li is over here, so if this is non-zero, then this will become a permutation of these guys, right? Because you have exactly k. Oh wait, yeah, it's not n, it's k. Right. Yeah, so that's the goal. So we want to show that f that there exists xi in Li such that f of x1, x2, xk is non-zero. And this is precisely the setting for combinatorial tangents. So what do we need? We need the coefficients, right? We want the coefficient of xi to the xi to the k minus 1, the product of that is non-zero, right? That's what we want. Now let's see why this is non-zero. And if you look at this term, what is the degree? So the degree here is k choose 2, right? And degree of this part is k choose 2. So you have a k choose 2 plus k choose 2. So k times k minus 1. Right? And which is the degree of this term, right? Right? So that means in order to have, yeah, so this is indeed the case. This is the one of the monomials of the highest degree. And in order to have that degree, you never use these AI, AJ terms. These are constant terms. So essentially what you need is to, so yeah, this coefficient, let me say this coefficient is equal to the coefficient of xi to the k minus y in, so let me ignore the AJAI terms, so then what you have is this squared. All right, now this is where we're gonna use the well-known determinant. If you remember this van der Monde determinant, then this is, so if you remember that from the linear algebra course, this is nothing but the determinant of 1, 1, 1, 1, 1, x1, x2, x3, xk, x1 squared, x2 squared, xk squared, and it goes until like x1 to the k minus 1, x2 to the k minus 1, xk to the k minus 1. All right, now this is, if we use the definition of determinant, what we get is something like this. Yes, sigma I. So for all permutations, so sigma is a permutation of 1 up to k. We make a product of sign and then take this term. So what is the, so how do we get the so we want to get the coefficients of this. Right, so just look at this product. Let me use different, yeah, so here it's so this is the first term and this is the second term. So now here is a tau product and x tau I and I minus 1. Now, when you choose sigma and tau, we're gonna have to choose in such a way that sigma I, right? So yeah, so sigma I has to be plus tau I has to be equal to I k minus 1. Maybe not. What's going on? So if I have xi minus 1 term, then I need to multiply by x to the k minus 1 minus I minus 1 term, right? So then if this is sigma I, so this is sigma I, but this sigma I has to be equal to tau of k minus 1 minus I plus 1. All right. Oh yeah. Okay. This is annoying, right? Maybe let's change this expansions. Let me write this way. So xi to the sigma I minus 1. So xi to the sigma I minus 1, xi to the tau I minus 1. All right, now it's easier. So we have I and then sigma I minus 1, and we have I and tau I minus 1. And we want their product to be something like x to the k minus 1. So xi to the k minus 1. So how is it possible? Well, we need to make this plus that to be k minus 1. So we're only interested in the case when tau I is equal to k plus 1 minus sigma I. Yes. But if this is the case, now we have two permutations, right? So if sigma is what is that? So that means tau is the reverse of sigma, right? If sigma is certain permutation, it's exactly the opposite. Right? So what's the sign? What's the sign of this permutation? So I claim that sine of sigma times the sine of tau is minus 1 to the k over 2 if k is even, and minus 1 to the k minus 1 over 2 if k is odd. But anyway, what we care is it's independent of choice of sigma and tau. Their product has always same value for fixed k. And why is this true? Well, the thing is, think of this way, right? So if this is, so let me say I put the first, I think of the matrix determinant. This is sigma 1, location of sigma 1, location of sigma 2, location of sigma 3, right? How do I get the tau? Well, if this was the location of sigma 1, I mean, it's just flip, right? So you flip left and right. So if this is a sigma 1, then this will become tau 1. If this is sigma 2, then this will become tau 2. Right? So if some 1 was on the first column, then it will become the last column, etc. So you flip the matrix left and right, right? So determinant of this is actually the sign of sigma. Determinant of that is actually just the sign of tau. But when you reversed columns, determinant will be differ by the depending on the number of columns, right? So if you have a k columns and you reverse the order, what's going to be the new sign? Well, if you have a even number of columns, then you swap first and last, second and second last, third and third last, etc. So you need change k over 2 times. You need swap k over 2 column pairs. So that's why you have a -1 to the k over 2. If k is odd, then the middle column is fixed. And the number of swapping is k minus 1 over 2, right? So you swap first column and the last column, second column with the second last column, etc. So that's why the product of sign is this. So this means that when we are only observing the coefficients of that, it's enough to look at this pair, right? So sigma and tau is then sign of sigma, and tau is given by that formula, right? Tau I is k plus 1 minus sigma I. So we are interested in the coefficients of the product of xi to the k minus 1 in this sum. Right? But this is already, this is what we want. So this is what? This is constant. Right? Either plus minus 1. So that implies that what we get is it's going to be plus minus 1 times the number of such permutations, which is n factorial. Oh no, k factorial. Right? So that's the coefficients. And since k is less than p, this is non-zero modulo p. Alright? So that means the coefficients is non-zero, so we can apply combinatorial stanza. By the combinatorial stanza, what we get is there exists bi in Li for all I such that, okay, so as we should say the b pi I in Li such that f of b pi 1 and b pi 2, b pi k is non-zero. Right? So that's it.